In this video, we're just going to quickly define what an acid and a base is before jumping into the more complex details of acid-base chemistry. So to begin, we have three definitions that we can follow. Beginning from here, the Arrhenius definition. So an Arrhenius acid is defined as a proton donor. So this could be any molecule that will donate a proton. For example, if we have this general acid, if it donates a proton, what's going to be left over is just A- and that proton over here. So an Arrhenius acid donates a proton, whereas an Arrhenius base donates an OH group or a hydroxide. So instead of having an H plus as a product with an Arrhenius base, we're going to see OH minus as our product. Now, that's pretty straightforward and simple, but that's not the common definition we use when we discuss acid-base chemistry. In acid-base chemistry, the more common definition of an acid and base is the Bronsted-Lowry acid and base. In a Bronsted-Lowry acid and base, we have the acid as the proton donor and the base as the proton acceptor. This is what we commonly see. Now, the last definition that we also have to quickly understand is the Lewis acid and the Lewis base. A Lewis acid will be the electron acceptor, whereas the Lewis base will be the electron donor. And here I'm just going to quickly draw out this equation again, where I have this, let's say, general acid, and I combine it with water, and I get the products A- and H3O+. So over here I can see that this was my acid because it had the proton, and we know that acids are proton donors. So it's going to donate the proton and it's going to become A-. So where does that proton go? The proton goes to this H2O, and the H2O then becomes H3O+. So we can see that this acid, it gained that negative charge. So since it gained that negative charge, it actually gained electrons. So that's why Lewis acids are electron acceptors. Whereas we can see over here that this H2O, it gained a positive charge, so it was the electron donor. I hope that makes sense. So these are the three definitions that we have to understand, and the most common one that we see in acid-base chemistry is the Bronsted-Lowry acid and base. Now moving on to over here, we see this equation once again, where we have our general acid with the proton, because remember, acids are proton donors. Then we have this acid combining in water, and we get the product A- and H3O+. Now remember, acids are proton donors, so it's going to donate its proton, and then we're going to be left with A-. That proton is going to be passed on to the base, and remember, the base is the proton acceptor. So when the H2O accepts that proton, it's going to become H3O+. It gains that positive charge because it gains that extra hydrogen over here. Now, the two other terms I want to introduce you to is conjugate base and conjugate acid. So when our acid lost the proton, it became a conjugate base. When our base gained a proton, it became a conjugate acid. Why do we call these conjugate bases and conjugate acids? Well, let's look at this reaction in the opposite direction. In the opposite direction, what's going to be our acid and what's going to be our base? Well, we see over here that we have this extra hydrogen, and if we pass that hydrogen over here, we're going to get HA and H2O. So this hydronium is actually going to give up an H+. And if it's giving up an H+, that means it's giving up a proton. If we're giving up a proton, that means we're an acid. So when the hydronium gives up that proton to A-, and A- then becomes HA, our A- is our base, and our hydronium is our acid. But we call them the conjugate, because in reality, if we look at the forward reaction, this is our acid and base, and then we get our conjugate base and conjugate acid. So essentially, if we want to go from acid and we want to get to our conjugate base, we just take away a proton. And if we're at our base and we want to go to our conjugate acid, we just add that extra hydrogen. Now here we can see the same thing going on in this diagram where we have this acid, and remember, an acid donates a proton. So if we want to get to the conjugate base, we have to get rid of one of the protons. So the acid is going to get rid of its protons and it's going to become OH. That's the conjugate base of H2O. Same thing over here. We have NH3 and we have ammonia, and ammonia becomes ammonium. And right now we have NH3, and this NH3 is actually gaining that hydrogen. Since it's gaining that hydrogen, once it gains it, it's going to become an acid. But before it was a base. So before it was just a regular base, and then it became a conjugate acid. We can actually see this reaction all together, where we take ammonia and we take H2O, H2O being the acid. Right over here we can see it's acting as an acid, and the ammonia acting as a base. We add these two in solution, and our H2O will become our hydroxide, and it will form a conjugate base, whereas our ammonia will become ammonium, and it will become NH4+, because it gains that hydrogen. Now lastly, we want to take a look at this diagram, which is essentially the same thing, and I'm just showing this once again to solidify the concept of what our conjugate acid and bases are. So here we can see that we have our acid. Our acid is going to donate a proton. It donates the proton and the base accepts the proton. So we had hydroxide over here, it gained a proton, and we got water. Whereas over here, we had 4 hydrogens attached to this nitrogen, and now we only have 3 hydrogens attached to the nitrogen. So we had our base, we had our acid. Acid donates the proton, base accepts the proton. When base accepts the proton, it becomes an acid, so it becomes the conjugate acid, whereas when an acid gets rid of one of its protons, it becomes a conjugate base.